Good afternoon, learners. I am Dr. Manish Bharadwaj from School of Engineering and Technology. As you remember, we were discussing about the design of flexural members in some of our last lectures. In some of our last lectures, we discussed about the flexural members, their behavior under the load, how these are designed, how the bending moment or the moment of resistance of these members is calculated, how these members are designed under the action of transverse loading. These were we discussed in some of our last lectures. In case of flexural members, we took first the case of a rectangular beam, then we took the case of a doubly reinforced rectangular beam, then we discussed about the design of flange beams. Till now we considered the bending moment only. Now, what other forces that comes to the member, that we'll discuss today. In case of RCC structures, members experience, in addition to the bending moment, shear force, and in some cases of course the torsional moment. So we will discuss about shear and torsion. How these two things, how do these two forces are taken care of during the design of flexural members. So first I'll discuss about the design for shear forces or shearing stresses. Now the question comes, when we say that we have to worry about the design of members for shear. So the question comes to the mind, where from the shear forces are coming. If on a structural member only and only bending moment is coming, then in that case the bending moment will be same throughout the length of the member. If this is the beam and only pure bending moment is coming on this beam, then in that case what will happen? Bending moment diagram will be uniform, and in that case no transverse shear force or shear stresses will come in the member. But generally this is not the case. Bending moment are always associated or accompanied by transverse loading. Because of this transverse loading, bending moment diagram is not uniform. Bending moment varies along the section of the member. Means from one point of the section or the member, it vary from one point to the another point. And due to this variation of bending moment on the structural member, what happens? Horizontal shear forces as well as vertical shear forces comes into picture at various sections of the member. Then next question comes, what is the effect of this shear force? If you can remember, you must have read in your strength of material course that when shearing shear forces are acting on a particular section. If this is a section and one force is acting on this side, one force is acting on downward, then under the action or under the effect of these shearing forces, what comes into the picture that we have to worry about is the tensile stresses that we generally call diagonal tension. So that you have already studied in your strength of material course. So if you can recall that, then the focus is that shear force, these shear forces acting on a section causes tensile stresses along the diagonal of a section, and these tensile stresses or diagonal tension causes tensile crack in the member, and because of these tensile stresses that cracks goes on increasing, and this may cause the failure of a particular member. So we have to worry about these tensile stresses. We have to counteract these tensile stresses. For that, we have to design our section to take care of these tensile stresses. So what now the question comes that how we can tackle these tensile stresses that are coming to the member. These tensile stresses are countered by the reinforcement that we provide in the form of vertical stirrups or inclined stirrups, or sometimes the bars, means the main reinforcement bars, these tensile reinforcement bars are also bent up to take care of these tensile stresses that are developed by the shear forces. So the reinforcement is the measure, providing the reinforcement is the measure that we apply to arrest these tensile cracks. Now, how to proceed for the design of the shear forces? So let us focus on the design principles, how we take care of these things. First is we find the shear stress that we generally call as nominal shear stress. It is denoted by tau V. This tau V is obtained by dividing the shear force by the effective cross-sectional area, B into D, where B is the width of the member, D is the depth of the member, and Vu is the shear force due to design loads. Means that shear force that we will calculate at particular section under the loads that are coming to the structural member. This expression is used for rectangular beams of uniform depth. Means, what is the meaning of it? That if the depth of the member is uniform, in that case only this formula will be applicable. Now you may come across the situation when the depth of the beam varies along the length. Now in that case this formula will not be applicable. Then for that case another formula we will see here. Here you see this beam for which the depth is not uniform. Depth is varying along its length. Here you see this is the load in the form of uniform distributed load as well as point load. This red color shows the main tensile reinforcement bar, and the angle which the beam is making with the horizontal, it is taken as beta. Here Vu is the shear force, design shear force calculated under the design load. Here due to the variation of bending moment, here this force H is coming. This H is the horizontal component of the force, tensile force that is coming in this bar. If we take the horizontal and vertical component of this T, then this is H and V. You see here the bending moment diagram. It is varying from 0 at the free end to the some value at cross section XX. This is the cross section XX. This JD is the lever arm. Two equal and opposite component of H are acting here, and as you see this is movement, bending moment applied at this section XX. So for this arrangement we will see that Vu is the shear force, whereas V, the component of this T, is acting in opposite direction. So the net force, shear force here comes out to be Vu minus V. This V can be taken as in the form of H, and from trigonometry you can write V equal to H tan beta, and H can be expressed as bending moment divided by the lever arm, because of this couple H, one acting in this direction and one in opposite direction, a moment is applied, and this H can be equated as Mu divided by JD. Now this JD can be written as equal to simply D, and this expression is the shear force at this cross section XX. You can write as Vu minus Mu by D into tan beta. So this is the shear force at this section. Now we have calculated the shear force acting on that section, so we can calculate the shear stress, nominal shear stress at this section, by dividing the shear force by the effective cross-sectional area at this section, means B into D. So here in general we can write as Vu minus plus Mu by D tan beta upon BD. This sign is minus plus. Here this is because of some software problem, this is mu is shown here, so read it as minus plus. So it is a general formula, and minus and plus these are for the two different situations. Minus for this particular situation that we see here, for a case when the bending moment is increasing along the section when the depth is also increasing. Means in this case, when depth of the beam is increasing as well as the bending moment is also increasing in that direction. So in this particular case we will take the minus sign in this expression. Whereas in the second case, if this depth is decreasing towards right, means opposite to this case 1, then depth will be decreasing along the length of the beam, whereas bending moment will be increasing. So in this particular case, in the second case, when depth is decreasing and bending moment is increasing, for this case this sign we will take as plus sign. So this is minus plus we are taking as a common formula for the two cases. So this we can prove. The second case also we can prove that positive sign will be taken in calculation of the nominal shear stress in this case of the beams where the depth is varying. So this way we calculate the nominal shear stress. First I told you about the case of the beams of uniform depth, and in second case I told you how to calculate the nominal shear stress in case of the beams where the depth is varying. So this was our first step, and this step is to calculate the nominal shear stress. Now we have to see that what shear strength concrete has, because concrete has its value to counter these shearing stresses, but this value, this capacity of concrete is limiting. So we have to take into consideration this limiting strength of the concrete to bear the shearing stresses. The shear strength of concrete increases with the better grade of concrete, means higher the grade of the concrete, then higher will be its shear strength capacity. Second thing is, in RCC the second material that we use is steel. So the percentage or the amount of steel also affects the shearing strength capacity, and higher the percentage of tensile reinforcement, higher will be the shearing strength of the concrete. So these two factors are important while designing or getting the value of the shear strength of concrete. First is grade of concrete, and second is percentage of or the amount of tensile reinforcement provided. And based on these two factors, code specifies the values of the design shear strength for concrete. In your IS 456 code, you will find a table in which design shear strength is given, tau C that we generally say. It is given against the percentage of tensile reinforcement as well as the grade of the concrete. So taking into consideration of these two things, the values of the design shear strength of concrete is given by the code. So when we will go for design of members for shear, we will refer this code from time to time to get the value of TOC from the code. Now, how to decide that how much shear reinforcement we should provide, and where it is to be provided, and in what form it should be provided. So let us discuss this thing, that how much and when the shear reinforcement is to be provided. So two things we have determined to this stage. First was nominal shear stress and second was design shear strength. By comparing these two values, we will reach to the conclusion that how much shear reinforcement should be provided. So in first case, if τ nominal shear stress is less than the design shear strength, means τ is less than τc. So in such situations, what we will do, we will provide minimum shear reinforcement, and this minimum shear reinforcement is specified in the code. This should be in the form that it should match this formula: ASV divided by BSV should be greater than or equal to 0.4 divided by 0.87 into Fy. Fy, you know, this is strength of steel, characteristic strength of steel or shear reinforcement. ASV, this is the area of stirrups. Stirrups are the shear reinforcement or steel that is provided in the form of a loop, and generally this loop is taken around and along the section. So generally two-legged stirrups are provided that we call vertical stirrups. So the area, cross-sectional area of these two legs of the vertical stirrups is denoted as ASV. B, it is the width of the member at that section. SV is the stirrups spacing along the length of the member. Means it is the spacing of these stirrups at which these will be provided throughout the length of the beam. So based on this, we will calculate ASV deciding upon the spacing, minimum spacing or maximum spacing. Now, in case of providing these stirrups, one thing you have to keep in your mind, that grade of steel you should not choose more than Fe415 for these vertical stirrups. Generally Fe250 is used. At the most you can go up to Fe415, not beyond this grade of the steel. So what is the contribution of this shear reinforcement? Means, why you see that nominal shear stress here is less than the design shear strength. So why we are providing the shear reinforcement? though it is, we are calling it minimum shear reinforcement, but what is the use of providing it? We provide this because this minimum shear reinforcement checks the growth of diagonal tension crack due to shear. This arrests the growth of the diagonal tension cracks, and also it increases the ductility of the flexural member. And as you know, by increasing the ductility of the RCC member, we are making our member, ensuring our member not to fail as a brittle failure, because brittle failure is a sudden failure and it does not give you enough warning before the failure. Whereas if there is any failure in the structure, then we will always desire that it should be a ductile failure, so that enough warning, enough time is there to evacuate from the structure. So this purpose is also solved by these minimum shear reinforcement. Now, the maximum spacing of the shear reinforcement, SV max, is also defined in the code, and code says that it should not be greater than 0.75 D, where D is the effective depth of the member at that particular section. So 0.75 D should be the maximum spacing, means this limit should not be crossed. It should be less than or equal to 0.75 D for vertical stirrups. In case of stirrups which we provide at an inclination of 45 degree, if we decide to provide the stirrups at an inclination, then in that case code says that maximum spacing should not be more than D, the effective depth of the section at a particular section of the member. Along with a rider, these limitations are specified in the code along with the rider, that in no case this maximum spacing should be greater than 450 mm. Means if the effective depth is more than 0.75 D or D, in that case may be more than 450, but maximum spacing should not be more than 450 mm. Now let's see the second case. Now if the nominal shear stress, calculated nominal shear stress, is greater than the design shear strength of the concrete, tau SE, then in that case what it indicates that the shear force is more than the design shear force that a RC member can take at that section. Means VU is greater than VC, and this you can easily find out if you multiply on both sides of this equation by BD. So tau V into BD will be greater than tau SE into BD if tau V is greater than tau SE. Here, for such cases, what we do, we have to provide shear reinforcement for the amount of shear force that is exceeding VC. Means the design shear force VUS we can determine by subtracting VC from VU. So we have to provide the shear reinforcement for the component of VU which is over and above VC, and that we denote it as VUS. Now, third case, if the nominal shear stress is more than the tau C max. Now, tau C max is the maximum design shear strength of the concrete, and this solely depend on the grade of the concrete. And in our code IS 456, a table is given based on the different grade of concrete, the values of their maximum design strength or the maximum shear stress tau C max is given there. Just like here, for some of the grade of concrete, these values are given. For M20, this tau C max is 2.8 Newton per mm square. For M25, it is 3.1 Newton per mm square. For M30 grade, tau C max is 3.5 Newton per mm square, and for M35 grade, this is 3.7 Newton per mm square. For M40 grade of concrete, tau C max is 4.0 Newton per mm square. So these are the value of maximum shear stress tau C max for different grades of concrete. So in such cases, in any such case, if nominal shear stress is more than the maximum shear stress for a particular grade of concrete, then in that case what we do, we redesign the section. We redesign the section up to the stage at which this tau V, nominal shear stress, becomes less than the tau C max. Because the situation when tau V is greater than tau C max is not acceptable to us. So we have to redesign such a section and bring the tau V to a limit which is less than the tau C max. So these are the three different cases that you may find while designing the flexural members. Now, shear reinforcement we provide, as I told you, to counter these shear stresses. But now let's see what type of shear reinforcement are provided. We provide the shear reinforcement, you may provide the shear reinforcement in three different forms. First is vertical stirrups, second is bent up bars along with the stirrups, means stirrups are also provided, and some of the bar of the main reinforcement, that is tensile reinforcement, these are bent up to take care of the shearing stresses also. Third arrangement is inclined stirrups. We can provide the stirrups in inclined form also. In first case, I told you that vertical stirrups means stirrups are provided in vertical position. Here in this case, you can provide the stirrups in inclined position. So these are the three different arrangements for providing the shear reinforcement. Now with this information, let's go for the design of shear reinforcement. Case 1. First case is when we provide vertical stirrups only. So in that case, the shear resistance of the shear reinforcement we can calculate as VUS equal to 0.87 Fy into ASV into D divided by SV. And this you can see from this picture. This is main reinforcement, tensile reinforcement. This is compression reinforcement or hanging bar. These in pink are vertical stirrups, and these are provided in the form of a loop. This you see here in blue, you see here the tensile crack that is developed across the depth of the beam, and for the case here you see that this crack is developed at an inclination of 45 degree, and this is the spacing which is kept uniform as SV, is spacing for the vertical stirrups. So for such case, shear resistance we can calculate from this formula. Second case is when bent up bars with vertical stirrups are provided, or stirrups are maybe also in form of inclined stirrups. But the case is here that means bent up bars in combination with stirrups. These may be vertical as well as inclined. So in this case, as you see from this figure here, this is the beam here, you see, and in this beam these some of the main reinforcing bars are bent up to take care of the shearing stresses. If the angle of inclination of these inclined bars or bent up bars is alpha, then in that case the shearing resistance provided by these bent up bars we can write as VUS1 equal to 0.87 Fy ASV1 into D divided by SV1 into sin alpha plus cos alpha. That you can derive easily from this figure. But this is the shearing resistance provided by these bent up bars. Now, as we are taking these bent up bars with stirrups also, so this is one part of the shear resistance. Some shearing resistance will be provided by the stirrups also. So here two parts are there: shearing resistance provided by the bent up bars as well as shearing resistance provided by the stirrups. So shearing resistance provided by the bent up bars we have written here. Second part, shearing resistance of vertical stirrups, that we saw in the first case in this formula. So VUS2 you can take it as. So summing up these VUS1 and VUS2 for vertical stirrups, we can find the total shear resistance of this shear reinforcement, where the shear reinforcement is here a combination of bent up bars and the stirrups. Now, in this particular case, code says that area of stirrups shall not be less than the minimum as specified in the code. Means whole of the shear resistance we cannot draw from the bent up bars. Minimum area of stirrups has to be provided. Second thing, code says that where bent up bars are provided, their contribution towards shear resistance shall not be less than the half of the total reinforcement. This is the provision in the code. Now, we know that inclined bars are ineffective in case of reversal of shear force. Means, if there is under some cyclic loading or under the effect of some variable loading, if there is a reversal of shear force, then in that case these inclined bars are ineffective, and also their exact behavior in resisting the shear force is still controversial. So because of these two facts, we generally do not prefer to provide the stirrups in the inclined form. We prefer to provide stirrups in the vertical form. Now, let's see the third case. Third case is if the inclined stirrups are only provided. Means no vertical strap is there, no bent up bars are there. Here only inclined strips are provided. For this case, you can easily determine the shearing resistance by using this formula VU as equal to 0.87 Fy into ASV into D upon SV into sin alpha plus cos alpha. So this is the shearing resistance when only inclined strips are provided. So that way we see the three different cases. Based on this information, based on this knowledge, now we can go for design of the shear reinforcement for flexural members, and this we will take in our next session. So with this information, you can go through your course material and find out what sort of problems are given in that your course material. Then if you feel any problem, then we will discuss the example problem in another session. Thank you.